Today we'd like to discuss the third part in our three-part discussion on determinants of order n. But first, let's review some ideas from before. We'd like to discuss what's called linearity in the rows. Let's say that V and W are two vector spaces. Given a well-defined map T from V to W, recall that the following statements are equivalent. First, T preserves addition and preserves scalar multiplication. That is, T of x plus y is T of x plus T of y, and T of C times x is C times T of x. Second, that's equivalent to T preserves linear combinations. Any map satisfying either of these equivalent definitions is said to be a linear transformation. Here's the main result that we'd like to come back to over and over again today. Let's say that we have an n by m matrix A. For each integer r between 1 and n, we'll define a function t sub r that takes a vector x to the determinant of b, where b is that n by n matrix obtained from A by replacing row r with this row vector x. We claim that t sub r is a linear transformation. In other words, the determinant of an n by n matrix is a linear function of each row when the remaining rows are fixed. Here's an example of this idea. Let's say that n is equal to 3 so that we have the determinant of a 3 by 3 matrix. When r is equal to 2, we have the following 3 by 3 matrix where we've replaced the second row with the vector x, y, z. We can now compute the determinant of b, and we'll call this our function t sub r in terms of the variables x, y, and z. We see that we can combine like terms together to see that t sub r is c1 times x, c2 times y, and c3 times z. This means that our function t sub r is indeed a linear transformation. Today we'd like to go over a couple of main properties about the determinant. First, we'll recall the definitions. Let's say that A is an n by n matrix. Recall that Aij tilde is that n minus 1 by n minus 1 matrix obtained from A by deleting the ith row and the jth column. We'll define the determinant of our matrix recursively as follows. When n equals to 1, then A is a 1 by 1 matrix, which we identify as a scalar. The determinant of A is just that scalar. If n is greater than or equal to 2, then we'll say that the determinant of A is a sum -1 to the 1 plus j times a1j, that is, this is the entry in row 1, column j of A, times the determinant of a1j tilde. That is, this is the determinant of that smaller matrix where we've deleted the first row and the jth column from our matrix A. Here's the main result for today. For any row I, we have the following expression for our determinant. It's a sum over j minus 1 to the I plus j times aij times the determinant of aij tilde. You'll see before in our definition of the determinant, I was equal to 1. Now we can prove that we have a sum where it does not depend which row I we choose. We'll say here that the determinant can be evaluated by a cofactor expansion along any row I. Second, the determinant of A is equal to 0 whenever A has a row of zeros. And third, the determinant of A is 0 whenever A has two identical rows. Let's try to prove these statements. We'll start by proving the second statement, what happens when A has a row of zeros. Recall that when we wanted to prove Theorem 4.3, we proved the following statement by induction. Let's say that A is an n by n matrix. Then for any integer r between 1 and n, we define this function t sub r of x that takes a variable x and returns the determinant of b, where b is that matrix obtained from A by replacing row r with this row vector x. The important statement here is that there exist coefficients c sub j such that t sub r of x is c1 times x1 plus c2 times x2, plus so forth through Cn times Xn. Let's assume now that A has a row R which consists entirely of zeros. That means that in the expression above, we can choose our vector x to be the row vector consisting of zeros, so that the determinant of A is simply C1 times the scalar 0 plus C2 times the scalar 0 plus so forth through Cn times the scalar 0, which of course equals the scalar 0. Hence, if A has a row of zeros, then the determinant of A must be the 0 scalar. Now let's go back and prove the first statement where we have our cofactor expansion along any row I. We'd like to prove the following proposition as a function of an integer n. Let's let B be an n by n matrix such that its ith row is the kth standard basis vector e sub k. Then the determinant of B is -1 to the I plus k times the determinant of b I k tilde. Before we try to prove this proposition is true, let's explain how this helps in proving the first statement. Well, row I of A can be expanded in the following way by using the standard basis vectors E sub j. That is, we can write A sub I, the ith row, as the sum over j of capital Aij times E sub j. Remember that capital Aij is the entry in row I, column j of our matrix, capital A. Let's let B sub j denote that n by n matrix obtained from A by replacing row I with the jth basis vector E sub j. Well, according to Theorem 4.3, since now we're looking at row I, we can then find some scalars, Cij, so that the determinant now we can expand along row I. But as we mentioned, row I we have here in terms of Aij E sub j, so we can write the determinant of A as maybe some scalar Ci1 times the entry capital Ai1 plus Ci2 times the entry capital Ai2, and so forth. Now, we have here our linear transformation T sub I coming from row I. So let's take our linear transformation and evaluate at the standard basis vector E sub j. Well, we can see here, just from some simple algebra, that Ti of E sub j is the scalar C sub ij. But according from the way we've set up these definitions, Ti evaluated at Ej is by definition the determinant of B sub j. Again, B sub j is that n by n matrix obtained by replacing row I with the standard basis vector E sub j. But now, the proposition above, assuming that is true, says that the determinant of B sub j is -1 to the I plus j times the determinant of B sub ij tilde. However, if we were to cross out row I column j, we really would just return the same as our matrix Aij tilde, because the way that we constructed B sub j is by replacing row I with something different. So our C sub ij is really -1 to the I plus j times the determinant of Aij tilde. We'll make a quick observation that we'll come back to later, that this here is exactly, by definition, the ij entry of the cofactor matrix of A. We conclude now that the determinant of A, which, according to Theorem 4.3, is a sum over j of some scalars Cij times the entries Aij, must be equal to the sum over j of -1 to the I plus j times the entry A sub ij times the determinant of Aij tilde. But this is exactly the statement in statement 1. Let's now return to proving that this proposition P of n is actually a true statement by induction. Let's start by establishing the base case. We claim that proposition P of 2 is true by simply looking at 4 cases. Remember that our matrix B is obtained by replacing row I with the standard basis vector E sub k. Well, when n is equal to 2, there are only two possibilities for I, that is, we only have two rows in our matrix B, and there are only two possibilities for k. That is, there are only two standard basis vectors, either 1, 0 or 0, 1. The table here shows the four possibilities where either I is 1 or 2, or k is 1 or 2, and we simply verify that the determinant of B is indeed equal to minus 1 to the I plus j times the determinant of Bij tilde. Now let's assume that the inductive hypothesis is true. That is, statement P of n0 is true for some integer n0 greater than or equal to 2. We're going to perform, finally, our inductive step. So let's consider proposition P of n0 plus 1. That is, we'll let capital B be an n0 plus 1 by n0 plus 1 matrix such that its ith row is the kth standard basis vector. We're going to consider now two cases. Case when I is equal to 1. We'll stare at the definition of the determinant, which is simply an expansion along the first row. Let's stare very carefully at B1j. This is the entry in the first row, jth column of B. Well, by the way that we've constructed B, remember that we've replaced row I with the kth standard basis vector. So in this case, because I is equal to 1, the first row of B is the kth standard basis vector. That means that our entry B1j should be the jth column of the standard basis vector. Well, if j is to the left of k, we have all zeros. And if j is to the right of k, we have all zeros. We only have a non-zero entry, which it turns out is 1, when j equals to k. So this explains the sum that we have on the screen. Let's consider next the case where I is different from 1, that is, I is greater than or equal to 2. We want to consider the matrix Bij tilde, which is that matrix we obtained from B by deleting the first row and jth column. Well, remember that row I is the one where we have our standard basis vector, so if we delete row 1, intuitively we're just moving all of the rows of B up by 1. I'd like to consider the I minus first row of B1j tilde. Again, we're starting with our matrix B, we're deleting the first row. So where we had row I now gets moved up to row I minus 1. But let's take a look at column J. Well, if we were to delete column J, we need to consider a few different cases. If J is to the left of K, then we've deleted one of the zeros that's to the left of 1. That means that our standard basis vector E sub k in B now becomes the k minus first standard basis vector in Bij tilde. When j equals k, this means that the column we're deleting to form Bij tilde is actually the number 1 in our standard basis vector E sub k. This means that the I minus first row now of Bij becomes a row of zeros. And finally, let's say what happens if j is to the right of k. Well, if we delete column j, now we're just deleting a 0 that's to the right of 1, and we're really not changing that standard basis vector. It's still E sub k. So this gives us a way to determine what is row I minus 1 of our matrix Bij tilde. Now we can compute the determinant of this matrix, but we want to be a little bit careful as to what we're doing. If we go back to the definition of the determinant, we have an expansion along the first row. Now let's stare at what's happening. Let's say that we want to compute the determinant of Bik tilde. Remember that this is what we get by deleting the ith row and jth column of Bi tilde. Well, if I is greater than 2, then along the first row, we just find the entries of B, namely B1J. We have to be careful not to look at B1K, because really we're just considering what happens when we delete column K. So we have a sum, Bij, where either J is to the left of K or J is to the right of K. But we do need to cross out row 1 in column J of Bik tilde. Again, this is how the definition of the determinant works with an expansion along the first row. But if we do that, if we delete the first row in the jth column of Bik tilde, this is just the matrix that we're denoting by Cij. Now, using the inductive hypothesis, we can stare to see that Cij is obtained from Bij tilde by deleting a row in a column, but remember that we actually do know that there looks like there is a standard basis vector in B1J tilde. We can just look at the formulas that we had before. Well, if I is less than K, remember that we had the standard basis vector EK inside of row I minus 1. So, because we had the standard basis vector EK minus 1 in row I minus 1, we have the formula you see here when J is less than K. When J is equal to K, remember that in row I minus 1, we had a row of zeros. So according to statement 2, the determinant here is 0. And finally, if J is greater than K, remember that in row I minus 1, we had the standard basis vector E sub K. So using the inductive hypothesis, we see the expression that you have here. Now let's put all of this together. Since the determinant of B1K is 0, we can now compute the determinant of B by looking at the expansion along the first row, and we simply realize that we really need to ignore what happens when J is equal to K because we just have a row of zeros. Now, we can take this expression here as we either sum to the left of K or to the right of K. We can substitute in what we had from the inductive hypothesis in terms of our matrix Cij. Now, by just combining the signs together in a clever way and using the initial expression we had for the determinant of Bij tilde, then we see that now this is actually an expression involving the determinant of B1J tilde. Hence, proposition Pn0 plus 1 must be true, which actually completes the proof of statement 2. Now let's finish things off by proving statement 3, which we'll also do by induction. We'd like to prove that if we have two identical rows, then the determinant is 0. So let's consider the following proposition. Let's say that A is an n by n matrix such that row R is equal to row S for some R different from S. Then the determinant is 0. When n is equal to 2, that is our base case, then it's easy to check that the determinant is 0 just by explicitly working out what happens when row 1 is equal to row 2. Let's assume now that our statement is true for some n0. We can now consider the inductive step. Say that we have an n0 plus 1 by n0 plus 1 matrix such that rows R and S are identical. Well, since n0 plus 1 is greater than or equal to 3, then we can choose I, R, and S, all distinct integers between 1 and n0 plus 1. In this case, we'll now consider an expansion along row I of our determinant. But now the matrix Aij tilde is a smaller matrix that has two distinct rows being equal, so by the inductive hypothesis, the determinant of Aij must be 0. But then this shows now, by looking at the sum, that the determinant of A is 0 as well. Hence, proposition n0 plus 1 must also be true. Thanks for watching.